All right. Welcome everyone to our next seminar today. I'm delighted to introduce Cara Giovanetti, who is a almost finished PhD student from NYU, who's been doing a lot of interesting work related to dark matter, new physics, and things like this. But specifically today, we're going to hear about Big Bang nucleosynthesis, and in particular, a new tool to study Big Bang nucleosynthesis. So thank you very much for logging on to be with us, and I will pass over to you. Thanks.
Great. Thank you. And thank you all so much for the invite. I was super excited to receive the invitation for this talk. I don't know how you guys usually do like questions during the seminar. I really welcome questions, but I am going to collapse the videos. And so please just like unmute and interrupt if you have a question. I really welcome that kind of thing. As Kieran said in that wonderful introduction, I'm going to be talking today about some work I've been doing on BBN, both some new physics investigations you can do with BBN and also some new tools that I've been developing to do better BBN analyses. And this is work that I've done with this long list of collaborators down here at the bottom of the screen at NYU and Princeton and Boston University. So the rest of the talk will be organized as follows. I'll start off with sort of the what and the why of BBN, and here I'll conclude that BBN is a powerful probe of both standard cosmology, lambda CDM, and of new physics. In the next section of the talk, I'm then going to talk about the kinds of new physics that we can learn about by studying BBN. In particular, in this talk, I'm going to be focused on portal models. So I'll give a very brief reminder of just some minimal portal models, and then I'll focus on two specific portal models that we can constrain with BBN. And in this section, I'll conclude that BBN still has a lot to say about new physics. And then finally, in the last section of the talk, I will talk about a new tool that I've been working on for BBN. And in particular, I'll show you that we can now perform sophisticated joint analyses with the CMB for the first time. So we'll start off again with why BBN, and of course before why BBN, obviously what BBN. So BBN is the period between 2 and 20 minutes after the Big Bang, where protons and neutrons are combining to form the first light element nuclei. It's an epoch characterized by high temperatures, so we're looking at energies in the MeV to keV range. This is sort of approaching the energy range you might start to see in a low energy particle physics experiment. But it's also characterized by very high densities. So the scale factor is something like 10 to the minus 10, what it is today. That means that the energy density in radiation, for example, is enhanced by a factor of something like 10 to the 40. And so you have very frequent interactions between lots of different fluids in the early universe. And then finally, it's also an epoch characterized by long time scales. And so it's also possible to probe things like weak interactions during BBN, which you can't always see inside of, say, a collider. And so BBN is highly complementary to what's going on in lots of different kinds of physics experiments that we do today. It is also an epoch characterized by very precise predictions and very precise measurements. So over here on the left, I'm showing an example of the kinds of predictions we can make during BBN. These are the abundances of several different light element nuclei as a function of time or temperature throughout BBN. Now, I don't show error bars on this plot. We typically don't show those as a function of time, but the error bars on the final abundances after BBN are something like percent level, and so we're getting very good at making figures like this one. Meanwhile, over here on the right, I'm showing an example of how we can measure some of these primordial element abundances. In particular, this is an absorption spectrum from a pristine gas cloud passing in front of a bright background quasar. So we know the emission spectrum of the quasar very well. So we can look at these absorption features to tell us about the relative abundances of different light element nuclei in this pristine cloud. And in particular, these absorption features over here on the left are telling us about the abundance of primordial deuterium in this cloud. So high temperatures, high densities, precise predictions, and precise measurements are all pointing towards the same thing, that BBN is a sensitive probe of both lambda CDM and of new physics. Now, before I jump in and start talking about all of the different kinds of new physics that you can learn about with BBN, I first wanted to just refresh some of the intuition for why BBN has this sensitivity. And the stars of the show for this next section, and really for the rest of the talk, are going to be helium-4 and deuterium, mostly because these are the nuclei whose abundances we can measure best, but it turns out that they have some highly complementary properties that make these more than sufficient for learning a lot about the state of the early universe. So helium-4 has a really large binding energy, and what that means is that once a neutron falls into a helium-4 nucleus, it doesn't really get out by the end of BBN. And so pretty much all to first order neutrons end up in helium-4 by the end of BBN. Now, if you look a little bit closer at 1 part in 10 to the minus 4, 10 to the minus 5, you also see some deuterium forming by the end of BBN. Deuterium has this really small binding energy, and so it's really easy to break it apart and incorporate its constituents into something heavier. And so deuterium will be really sensitive to any physics that causes baryons to interact more frequently, since that'll cause deuterium to get broken up. So in terms of the specific physics, I'm going to start on the helium-4 side because I think it is a little bit more familiar, and then I'll move on to talk about deuterium. So the helium-4 abundance is going to be sensitive to your neutrino temperature and your expansion rate. Let's take a look at why. So these are the reactions governing proton-neutron interconversion in the early universe, and we see right off the bat there are neutrinos involved, and so we expect these rates to depend on the neutrino temperature. Meanwhile, we can write down the equilibrium number density of neutrons relative to protons. It's just Boltzmann suppression because the neutron is a little bit heavier. And so we can write down a prediction for the number density of neutrons in the early universe that looks something like this. So at these high temperatures, we're characterized by this equilibrium curve, and then at some point, these reactions will freeze out and the abundance of neutrons will stabilize. If, however, we have colder neutrinos, or maybe the universe is expanding more quickly, we might freeze out earlier and therefore have more neutrons relative to protons. And this will translate directly to a larger abundance of helium-4. So crucially here, we're freezing out higher up on this equilibrium curve, and so we get a higher abundance of neutrons relative to protons. This is pretty much the entire story as far as helium-4 is concerned. I can move on to talk about deuterium unless there are any questions. Great. All right. So the deuterium story is a little bit more complicated. So it is also going to be sensitive to the neutrino temperature and the expansion rate, but the mechanism is a little bit different. This is all going to go through N effective. So if you need a refresher, N effective is the effective number of neutrinos in your cosmology. It's the energy density of radiation. You subtract off the energy density in photons, you divide by the energy density in one neutrino, assuming that neutrino decoupled instantaneously, and that gives you this effective number of neutrinos, which in standard cosmology is roughly 3, since there are 3 neutrinos and 1 photon in this row R. In this talk, I'm going to be using N effective and expansion rate pretty much interchangeably, since we're deep in radiation domination, and so Hubble is pretty much just determined by this row R. Now, because N effective depends on the photon and neutrino energy densities, I can rewrite it in terms of the relative temperatures between these two species. And so we see that if I change the neutrino temperature relative to the photon temperature, that's going to translate to a change in N effective, and therefore a change in the expansion rate of the universe. Now, I'm also going to leave the door open for there to be this extra dark radiation. So this is beyond standard model. This is an extra piece we would add to this rho radiation in some BSM model. It doesn't couple to anything. It's totally inert. And its only purpose in life is to increase the expansion rate of the universe. This will be important a little bit later on when we start talking about some BSM models. But again, this is going to show up in our prediction for the deuterium abundance through the expansion rate. So why is deuterium sensitive to the expansion rate at all? This is because if the expansion rate is too fast, there's no time for heavy elements to form. So if the universe expands very slowly, BBN proceeds like this, where you start off with your protons and your neutrons, BBN starts, you start to form your deuterium, and then everything is really close together, so it's really easy for deuterium to bump into something else, get broken apart, or get incorporated into something heavier, and so we can proceed all the way up the chain. So in this scenario, we have eaten up all of our deuterium and formed heavier elements with it. If, however, the expansion rate is a lot faster, then we're able to form our deuterium, but now the universe is expanding so quickly that there's just no time for deuterium to find something else to bump into, and so it is able to persist all the way until the end of BBN. Now, there's one more effect, and it's going to look very similar to this one, though the mechanism will be a little bit different. This is an effect from the baryon to photon ratio. I've written that here as eta. I will use that interchangeably with omega b for this talk. If the baryon to photon ratio is large, if there are lots of baryons and not very many photons, then again, these baryons have no trouble finding one another, bumping into each other, breaking the deuterium apart, and incorporating it into something heavier. And so again, here we deplete all of our deuterium to make something heavier. But if there are a lot of photons relative to the number of baryons, then it's just sort of like there are fewer baryons per unit volume. There's less stuff for the deuterium to bump into, and so it's able to persist until the end of BBN. And so the dominant effect here will again be more deuterium. So to summarize all of that, there are many potential signals that show up in BBN. If you change the expansion rate, you're going to impact your prediction for helium-4 and deuterium. If you change the relative photon and neutrino temperatures, you make the weak rates freeze out earlier or later, or you can have a direct effect on an effective, which feeds back into the expansion rate. And then finally, there's this baryon to photon ratio effect. Deuterium actually ends up being so sensitive to the baryon to photon ratio that it provides a complementary probe of this parameter as compared to the CMB. And the precision of the BBN determination of eta is approaching that of the CMB. They're both roughly percent level. And so this is highly complementary to CMB analyses. You measure a lot of the same parameters, and it's a totally independent epoch of cosmology. And then again, as I'll talk about in the last section of this talk, there are new tools that I've been working on that make really rigorous BBN analyses now possible. So I hope that was convincing that BBN is a powerful probe of your cosmology. I want to move on and talk about how BBN can
Could I
inform new physics.
break in with a question
Please do.
about that? So, I mean, all of that is very well taken, and you're speaking about the connection with expansion and so on. But for deuterium and with photons specifically, rather than other forms of radiation, in a specific range of temperatures, you've also got photons that are energetic enough to dissociate the deuterium, and that's because the binding energy is so very low.
Right.
That's an effect that's specific to deuterium rather than to other species. I mean, you can construct a photon spectrum that will dissociate deuterium and it won't dissociate other things.
Right.
And so in a regime where the temperature in general is falling, that creates a window in temperature where there are distinct effects around the rate of the number of photons as opposed to other radiation that, I mean, for its spatial effects, radiation is radiation. It doesn't matter if it's photons, neutrinos, if it's dark. Deuterium very much cares.
That's
so
right.
You didn't speak to that. Do you want to just sketch out what the distinct effect is there?
Yes. So, I mean, the only difference, and you're absolutely right. So here, you might worry that if the baryon to photon ratio is small, you have all these photons floating around. You might have some high energy photons in the tail. Can that just break apart deuterium? The answer is absolutely yes. It turns out to be subdominant in this sort of like standard cosmology picture. If you had some like new physics that was really distorting the photon spectrum, like sometimes people think about like dark photon oscillations in the early universe producing these high energy photons that can break apart deuterium, then absolutely yes, that is another effect. I won't be considering those scenarios too much in the rest of this talk. The only other thing I can say about it is that there's this new code called Acropolis that is specifically written to handle things like photodissociation. So if you have like a new physics idea in mind, it would be really easy for you to just compute the effect of that on BBN.
Because it would seem, I mean, there's a generic set of scenarios where something creates a non-thermal tail in the spectrum, and that can produce radical change.
That's absolutely right. So in this talk, I'm only going to be thinking about dark matter or electromagnetically coupled dark matter that's thermally produced. And I'll show you the specific model I'm thinking about in a couple of slides. You are absolutely right. That is another effect that you might have to consider. It didn't turn out to be relevant for the scenarios that I'm going to be talking about for the rest of this talk.
Okay, so it's a question of emphasis and focus. Okay, thank you.
Exactly. Yeah. Thank you. Okay. Any other questions before I move on?
Maybe
Great.
I can just
Please.
quickly. So I'm not sure how much this will come up, but all the rest of the chain of nuclei. I guess is the story just sufficiently complicated that it's not really capturable in terms of just a simple diagram? I guess you're going to be including all of those in the analysis because you
Yes.
have predictions for them.
Yes.
But is there any simple intuition for like how things affect like the various other nuclei? I mean, lithium, for example, where there's this like supposed problem and so on.
Yes. Good question. So again, I'm not going to talk too much about the lithium problem, just to focus on that specific nucleus for a second. There's some debate about whether the lithium problem is a cosmological tension or just like a misunderstanding of how lithium behaves in stars. And that's sort of moved into the domain of astrophysics, at least for now. And so I won't be commenting much on that. But you're absolutely right that we do have to consider other reactions up the chain. So just because we're only going to be focusing mostly on helium-4 and deuterium, that doesn't mean that we don't also consider reactions that involve heavier element nuclei. And in fact, like we can't make these predictions about deuterium unless we're also incorporating effects from having these heavier element nuclei depleting all of the deuterium. And so that absolutely will be included. It's mostly going to be under the hood. In the next subsection, I will show you a picture of the reaction network that we use to get up to helium. Turns out you only need about 12 reactions to accurately predict up to helium-4. But you do need to go up to like lithium, beryllium in order to get that all accurate.
Yeah, so maybe I'll butt in a bit more on that, maybe just following up on. So you're not worried about anything with lithium or what lithium, like the whole lithium problem. Okay, but regardless of what the lithium problem, status of that problem is, so your analysis, so the dominant effects that you're considering is up to deuterium, nothing beyond.
I'm sorry, I don't know that I understand the question. What do you mean by after deuterium?
So in the sense that, are you also concerned about, effects on lithium abundance or something? That was the
Good. So when I construct my likelihoods, I do not include a term for lithium. So I effectively, I'm just assuming that like maybe the lithium problem is a stellar problem, or at least I'm sort of sweeping it under the rug for now. And I'm not going to consider any kind of lithium tension when I go ahead and do my analyses.
All right.
Anything else? Okay, great questions. Good. Okay. So I mentioned at the beginning of the talk that I was mostly going to be talking about portal models when it comes time to talk about some new physics. So just to give a very brief reminder of portal models in case anybody on the call is not familiar, the basic idea is that you have the standard model on one side, you have your dark sector on the other side. This often includes dark matter, but can also include other states. And then you have a new field that acts as a portal between each sector. Just some examples of minimal portal models you may have run into in the literature. You might have a vector portal, so you have some new gauge field that has a kinetic term mixing with a standard model gauge field. You can have a neutrino portal, so some new heavy neutral lepton that mixes with the standard model neutrinos. You can have a Higgs portal, so some new scalar that couples to the Higgs mass operator and then will couple back to the dark sector. And you might also have an axion-like particle portal, so you have some ALP that couples to photons or gluons. So these are just some sort of minimal canonical examples that you might be familiar with. In this talk, I'm going to give you an example of a vector portal and a neutrino portal that we can constrain with BBN. So the first specific model that I want to take a look at is this one, which should also probably be pretty familiar to many of you. This is sort of the standard dark photon Lagrangian. I have some new U1 prime gauge field, A prime. It has a mass for our purposes. I'm going to take that mass to be roughly MeV scale. And it has a coupling to the standard model electromagnetic current through this tiny coupling epsilon. In addition to the terms I've shown here in this Lagrangian, we also are going to have some massive dark matter chi. It will also have an MeV scale mass. I left the term out of Lagrangian because I want to be agnostic as to whether it's scalar or fermion, but it's there. And then finally, I'm also going to leave the door open for there to be this dark radiation. We're adding these new light fields to our Lagrangian. It is not out of the question that there might be some other new inert fields hiding somewhere in our dark sector. And so we'll sort of leave the door open for this to be in our model. So this is an example of a vector portal. If you're interested in the history or not familiar, this was originally linked to this galactic center excess. It has since been ruled out as an explanation for this particular excess, at least in the most vanilla versions of this model. But along the way, it's become this really common experimental benchmark. So it also has its own well-motivated theory motivation. And so when experiments report their sensitivities, they are often reporting their sensitivities to this model of dark matter. And so it would be great if we could get some complementary constraints coming from cosmology that we could report alongside these experimental sensitivities. So why does BBN care about this model? I think I can summarize that in just this simple Feynman diagram. So we have dark matter annihilating to our dark photon, and then that decays into an electron-positron pair. Now, there are three main effects that this will have on BBN in some different regimes. So if the dark matter mass or the dark photon mass are really light, then these species are just acting like dark radiation. They're radiative through all of BBN, and so they contribute directly to N effective. They cause the universe to expand more quickly. And we're going to see this show up in our prediction for helium-4. So on the x-axis here, I'm showing the dark matter mass. For simplicity and illustration, I have set the dark photon mass to be equal to the dark matter mass, but that's just a choice that I needed to make these curves. And then on the y-axis, I'm showing the helium-4 abundance. I'm using this slightly historical notation, Yp, for the helium-4 mass fraction, but it's just one-to-one with the number abundance of helium-4. And we see that as the dark matter mass gets lighter and lighter, these species are acting more and more like radiation for more and more of BBN. And so the universe expands more quickly. We freeze out higher on that equilibrium curve, and so we get more helium-4 overall. Okay, now what if we had a slightly heavier mass and it wasn't just acting like dark radiation through all of BBN? Then the dominant effect is this one. When the dark matter freezes out, its entropy has to go somewhere, and because of this coupling, the entropy is going to go into the photon sector. We're going to heat up the photons. Now, given that, cosmological events happen according to the photon temperature, what we see is not that the photons are hotter, but that at a given photon temperature, the neutrinos are colder. And so the dominant effect here will be colder neutrinos relative to photons. And we're going to see this show up in our prediction for deuterium. So once again, I'm showing the dark matter mass on the x-axis, and now I'm showing the deuterium abundance relative to hydrogen on the y-axis. And in this intermediate mass range, I have heated up my photons or cooled off neutrinos. The universe expands more slowly. There's more time for deuterium to bump into other things and get broken up and incorporated into something heavier. And so we get less deuterium in this region of parameter space. There's one last effect, and that's again at very low masses. If the dark matter is so light that it's annihilating after electron-positron annihilation, it's going to cause some late time changes to the baryon to photon ratio. So all of the electrons and positrons generated by this late time annihilation will eventually annihilate to photons, and so the baryon to photon ratio has to get smaller after BBN. But we measure the baryon to photon ratio today, and so it had to be higher during BBN to account for this late time photon dump that happens in this model. And so here we see this again in deuterium at these very light masses. The baryon to photon ratio is higher during BBN. The baryons are closer together. It's easier to break apart deuterium, and so we deplete our deuterium abundance. The punchline of all of these details, in case you're falling asleep on me, is that deuterium production decreases with decreasing dark matter mass, but the helium-4 production will increase with decreasing dark matter mass. And this opposite behavior is going to be really important in just a couple of slides. Now you might be thinking, but Cara, you're changing N effective. Why don't you just use the Planck determination of N effective to put constraints on this model? And the reason is that there is one player in this game whose role we have not yet explored, and that is this dark radiation. So if you recall our parametrization of N effective from earlier, if there's no dark radiation in our model, then this is really simple. We're injecting all this entropy into photons, we're heating them up, and so we see a corresponding decrease in N effective. But if my model also has this dark radiation, it allows me to reduce or even eliminate this effect on N effective. So there's this degeneracy between the change in the photon temperature and the amount of dark radiation in the model. And I can show this pictorially. Here on the x-axis, I'm again showing the dark matter mass. On the y-axis, I'm showing the prediction for N effective in this model, and the colored bands are the 1 and 2 sigma measurements of N effective from Planck. The solid curve is showing what happens when there is no dark radiation in the model. And again, it looks like there's a constraint. Around 5 or 6 MeV, we cross over the 2 sigma threshold of this N effective measurement, and it looks like the dark matter just can't be this light in this model. But now, if my model also has this dark radiation, there's a lighter set of masses that are allowed. And so there is this degeneracy here that prevents me from putting an absolute lower bound on the mass of dark matter in this model. Fortunately, BBN is going to come in and save the day. So adding dark radiation has the same effect on both deuterium and helium. On the deuterium side, you are making the universe expand more quickly. There's less time for deuterium to bump into something else and get broken apart, and so we get more deuterium. On the helium-4 side, again, the universe expands more quickly. We freeze out higher on that equilibrium curve and get more neutrons overall. Now, on the deuterium side, it sort of looks fine. Like we've pushed this curve into the measured region for deuterium, and so it sort of looks okay. But in so doing, we have completely ruined our prediction for helium-4. And so using this information from BBN lets us break this degeneracy between the photon temperature and the amount of dark radiation in the model. And so we can summarize this into a nice constraint. So here in gray, I'm showing some existing constraints from things like direct detection or beam jump experiments. And over here, I'm showing the new constraints that we get with BBN, and then also using the Planck determination and Simon's projection for N effective to get some slightly tighter constraints. And we see that this is highly complementary to experiment. We're able to get some information about this region of parameter space that is famously difficult to probe with things like direct detection and beam jump experiments. And all we're doing is using some sort of low-hanging fruit measurements we've already taken that come from cosmology. Are there any questions on this before I move on now to the next model that I want to talk about?
Yeah. Oh,
Go ahead.
go ahead, Divan.
No, go ahead. No worries. You go first. Oh, sorry. Did you want me to go first? I was just...
Yeah, go ahead. Divan,
Yeah.
your mic is really,
wondering,
really suffering. So just maybe speak up.
Yeah, sorry. So you're dumping a lot of electrons through the portal at some late time. So are you also plotting the energy injection constraints on this, or is that not relevant here?
Do you mean like an energy injection constraint to the photons?
Yes, in the sense that you're dumping a lot of electromagnetic radiation. So I expect things like spectral distortion, if it's relevant, that is, within at least
No, you don't.
that you're looking at.
Yeah, no, the spectral distortions you don't really get. You're much too far from the CMB to be able to see this. This is all happening at much higher redshifts.
I see. Okay.
Kieran, you had a question?
Yeah, the question I had was, so how do I understand the fact that your constraints are not sensitive to the electron cross-section?
Good.
So your specific choice for the dark photon mass and so on? Or...
Yeah, so they are sensitive. It's just that the sensitivity only kicks in well below the cross sections I've shown here. It's something like 10 to the minus 46. So the key assumption is that you're able to thermalize your dark sector. And so any coupling that you're able to thermalize the dark sector at, our constraints apply fully. Once you're no longer able to thermalize the dark sector, then the calculus changes a lot. And so that happens well below the region that I'm plotting here. So it's sort of an all or nothing with this sort of transition region, and I'm just showing the region where we know that they apply.
And so your constraints from, like, for example, xenon 1 ton, I mean, typically when they set these constraints, they use like the heavy mediator or light mediator limits.
Good.
You've got a specific choice for the relationship between M chi and M a dash. So is this just a self-consistent comparison that you're making?
Yes. Yeah. So we pulled, for all these experiments, we pulled their results, assuming this particular relationship between the two masses. You're right that they also often report the other ones, and we didn't test those. Yeah.
Okay, thanks.
Great. Anything else? Okay, I'm going to move on. If there are any other questions, feel free to just jump in. So before I can jump in now and talk about a different model of dark matter that we can learn more about using BBN, I need to take a brief detour and talk about a potential mild tension in primordial deuterium. So a couple of years ago, this group led by Cyril Petro that has written a really precise BBN code was finding that their prediction for primordial deuterium was about 2 sigma lower than the measured value. Now, a 2 sigma tension is not a tension. It is not a crisis for cosmology. But the measurement of deuterium is statistics limited. And so there's a concern that as we get more and more measurements and these measurements, the measured value gets more and more precise, that this is something that could get a little bit worse. And so it's worth keeping an eye on. The other important thing to note about this tension is that it's not just a tension between measurement and prediction in BBN. You can also think about it as a tension between the BBN and CMB determinations of the baryon to photon ratio. So if you look up BBN in the PDG Review of Particle Physics, you'll be greeted by a beautiful Schramm plot that looks like this. And here, in blue, they're showing their prediction for primordial deuterium as a function of the baryon to photon ratio. And so you can infer a value of the baryon to photon ratio by looking at the measurement for deuterium, that's the height of this tiny little yellow rectangle, and finding all of the values of the baryon to photon ratio that make that measurement consistent with the prediction, so the width of this blue curve. And so that leads to this pink hatched region here. That is the BBN prediction for the baryon to photon ratio. Very helpfully, they've also shown the CMB determination of the same parameter. Here is this cyan rectangle. And so here they're saying that there's no tension. Both of these determinations of this parameter agree. If, however, you had a slightly different prediction for primordial deuterium, and this is a bit of an exaggeration, say now your prediction is a little bit lower, the measurement doesn't change. And so now you have a new range of baryon to photon ratio values that are consistent with measurement, and suddenly you have this tension between what BBN prefers for this parameter and between what CMB prefers for this parameter. And so this distinction is going to be really important in just a couple of slides. We can see this as this tension between these two different epochs of cosmology. Now, the other thing to take away from this plot is that PDG is saying that there is no deuterium tension. So why are some groups saying there's a tension and others are not? And the main difference is just coming down to what people are choosing for their reaction networks. And Kieran, this is getting back to your question from earlier. So the main input to any BBN code is a reaction network. This includes experimentally determined rates for all of the reactions that are active during BBN. And so you can make a little cartoon of a reaction network that looks like this. So you have some experimentally determined rate that is taking you from protons and neutrons to deuterium. And then there's some other rate that takes you to tritium, or 2 other rates that take you to helium-3 and to helium-4 and all the way up the chain. Now, nobody disagrees about what reactions should be included in the network. So everyone would draw the same picture for their reaction network. And nobody really disagrees about what experimental data should be used either. The main point of disagreement is how the nuclear physics data is treated. And what I mean by that is that there are regions of parameter space where these rates need to be interpolated or extrapolated, and the data treatment leading to that interpolation or extrapolation can differ quite a lot between different groups, and it's not obvious a priori which one is correct. And so at this stage, the absence or presence of this mild deuterium tension is due entirely to your choice of a reaction network. So for the next 2 slides, we are all going to be deuterium tension believers. We are going to believe, 1, that the deuterium tension is going to get worse and approach 5 sigma level, and we are going to believe, 2, that the reaction network that produces the deuterium tension is the right one to use. In 3 slides, we will relax that assumption. So the deuterium tension is a crisis. We need to solve it. How might we be able to solve a tension like this with new physics? The model we're going to use looks like this. So we will have some dark fermion. Again, it's going to have an MeV scale mass, and this is effectively a sterile neutrino. So we also are going to have this mixing term between our dark fermion and our standard model neutrino. So we're going to start out with our dark sector unpopulated. We will equilibrate our dark sector via repeated oscillation and scattering with these standard model neutrinos thanks to this term. Now, at some point, the dark fermion is going to freeze out, and it's going to do so at a temperature I will call T step. And the reason I'm calling it T step is that it's going to produce a step in N effective. Reason being, we also have this light scalar that couples to the dark fermion. And so when the dark fermion freezes out, it pumps its entropy into this very light radiative degree of freedom, and so it increases N effective at this late time. Now, you might also worry, but don't you also put some energy into the standard model neutrino? The answer is yes, but it's going to be very subdominant to this N effective effect that we're going to be focusing on in this region of parameter space. So I can show you the evolution of N effective as a function of temperature. We start out with some small value of N effective, we pass through T step, and we end up with a larger value of delta N effective than we started with, just because this dark fermion froze out and put this entropy into this radiative degree of freedom. Now, you might be thinking, but you just told me that if you increase the radiation energy density, you increase N effective, you ruin your prediction for helium-4. And to that I say, if you have a step in N effective, you have a chance to modify deuterium and not touch helium-4. And here's why. So this, again, is the abundances of different light element nuclei as a function of time or temperature. The purple curve here is showing the prediction for helium-4. And we see that in this window, I've shown that the helium-4 prediction is starting to stabilize in this region. But the deuterium prediction, shown here in green, is still evolving. And so if I change my physics somewhere in or around this window, I'm modifying the physics that's still very busy determining the deuterium abundance, while helium-4 is sort of agnostic to any of these later time changes. So the punchline is that this works. We found that it worked across a surprisingly wide range of step temperatures and changes to N effective. There is a caveat that arose when we did this analysis that I think is very interesting and I want to talk about on the next slide, unless there are questions on this lightning overview of how this model is working. Okay. So,
Yeah, sorry.
Yeah, please. Go ahead.
Cara,
Thank you.
it just took me a moment to find the controls. So quantitatively, that's because the deuterium abundance is by that stage sufficiently low relative to the helium abundance that even if you do things that vary it, the helium abundance doesn't change that
Right,
much.
yeah. Like if I showed this on a linear plot, yes, you would still be like seeing a lot of evolution in helium.
Right, just because I mean, if you up the amount of deuterium and then deuterium interacts, then everything ends up in the helium-4 drain. And so I'm just trying to understand why you can affect one and not the other. But it's basically because at this point here that you show, they're already an order of magnitude apart, and so it becomes hard for one to influence the other. That's the point.
That's right. Yeah.
Okay. Thanks.
Great question, and thank you for clarifying. Anything else? Okay. So we started to run our. Oh, how can I get rid of the?
I'll get rid of it. Sorry.
Thank you. Okay. So we started to run our scans, and we were getting results that looked like this. And we were really excited to see this. We were seeing a preference for a non-trivial step temperature and a non-zero change to delta N effective at a significance greater than 2 sigma. So you're like, great, this is only a 2 sigma tension, so that's, pretty good. But then we realized, well, okay, this is the reaction network that has the deuterium tension. And so we should probably also use the reaction network that does not have the deuterium tension. And there, very predictably, any kind of significant preference for this model went away. So standard cosmology is the asymptotic limit of this corner of the plot. And so there's no region of parameter space that's preferred over standard cosmology at anything remotely significant. But the plot thickened even from there. So you'll remember that I said that the deuterium tension is really a tension between the BBN and CMB determinations of the baryon to photon ratio. The CMB determination of the baryon to photon ratio is model dependent. The CMB does not measure omega B. The CMB measures anisotropies on the sky. And then you have to assume an underlying cosmology in order to get a result for the baryon to photon ratio. And so if I pick lambda CDM versus lambda CDM plus N effective versus lambda CDM plus N effective plus sum of neutrino masses or something more exotic, I can get some very different determinations of the baryon to photon ratio. And so what we found we really had to do was also vary the prior on the baryon to photon ratio that comes from the CMB. So the value of that prior is shown on each plot as this omega B star. And so we found that if we chose this sort of middling value for omega B, then any preference for this model completely evaporated. This now turns into an exclusion plot where we're just excluding regions of this parameter space at greater than 2 sigma. And if we choose this low value of omega B, then we start ruling out this model in pretty large regions of parameter space. And so what we found here is that in order to explore this tension, not only do we have to explore the systematic from different reaction networks, but we also need to be ready to scan over a number of different fiducial cosmologies. And the problem is that this is really hard. So switching reaction networks is really important, but it's very difficult. Oftentimes the reaction network is hard-coded into the BBN code that you're using, or they'll only ship with one reaction network. And so if you want to check the other reaction network, it's a significant investment. Meanwhile, some of the plots that I've shown so far in this talk took upwards of 6 days to generate, and so these are not efficient or fast analyses. And then finally, I haven't really touched on this that much yet in this talk, but calculating theory uncertainties in BBN is also really hard. A lot of the public codes either aren't really set up to do it in a very principled way, or the codes are really slow, and so if you also now want to start calculating your uncertainties, it just multiplies the amount of time it takes in order to do these analyses correctly. And so this is going to take me to the last section of my talk. So far, I hope I have convinced you that BBN is a great probe of cosmology, and it still has a lot to say about new physics. In the last section of the talk, I want to talk about some new tools for BBN, with the punchline going to be that there are now sophisticated joint CMB and BBN analyses we can do for the first time. I see I'm running a little low on time, but are there any quick questions before I jump into that? Okay. Good. So the goal of this new tool that we developed for BBN is first and foremost to have a fast BBN code. We want you to be able to run this code 10 million times and have that not take months to years. We want it to be easy to calculate your theory uncertainties. It should not be difficult to determine any kind of statistical uncertainty that's coming out of your BBN reaction network. And then it should be easy to switch between different reaction networks. You should be able to explore this systematic without really breaking a sweat. The point of all of this is to put BBN analyses on the same footing as CMB analyses when it's time to do parameter estimation. So you want to estimate omega B, you want to use BBN and the CMB. We don't want BBN to be the bottleneck in that analysis. And we don't want your results to somehow be less trustworthy because you weren't able to explore all of the sources of uncertainty on the BBN side of that analysis. Now, this is going to involve introducing a lot of new nuisance parameters to your cosmological analysis. So nuclear physics is giving us an uncertain rate for each of the reactions in this network. And so it is not good enough to just use the median values for all of these rates. You also need to sample these rates as nuisance parameters. You need to see what happens if you're 1 sigma high or 1 sigma low, or you need to do an MCMC analysis to sample all of these different parameters. And again, this is going to involve introducing at least 12 new nuisance parameters to your cosmological analyses, since you need at least 12 rates active in order to accurately predict up to helium-4. So if you tried to do an analysis like this with an existing BBN code, you might run into a couple of hurdles. So you might try to use a code like AlterBBN. AlterBBN is written in C, which makes it really fast, which is good. But unfortunately, it is no longer really state-of-the-art. Their implementation of neutrino decoupling is a little bit out of date. They're not using all of the most recent nuclear physics data in their reaction network, and so it really is in need of an update if you're trying to do precision BBN with this code. You might try to use Premot. Premot is written in Mathematica, which makes it very accurate, but also very slow. They pioneered a very precise treatment of proton-neutron interconversion. They have a very large reaction network that they can use to predict up to carbon, nitrogen, oxygen, but at a minute per solve, it is just too slow for this kind of parameter estimation. Okay, so you might try to use parthenopy, which again is really fast. It's written in Fortran, but it's not quite set up to be able to do this MCMC type sampling of the reaction rates. You'd have to hack its guts, and given that I draw the line at Fortran, I was not really willing to do that. And then finally, you can try to use primordial. Primordial inherits a lot of the accuracy of Premot, and so it's very accurate. It is possible to do the kinds of full parameter estimation that we have in mind with primordial, but at 10 seconds per solve, it is just a little bit too slow for this kind of analysis. Now, Kieran told me that Anne-Catherine gave this seminar a couple months ago and hopefully told you about all of the benefits of using primordial. But if you're going to try to use it or any other kind of existing public BBN code to do this kind of parameter estimation, you're going to have to make some kind of compromise. And I'll talk a little bit more about what those compromises look like in a couple of slides. So we wrote a new BBN code. It's called LINX. LINX is written in Python, but also uses JAX, and I'll talk about what JAX is on the next slide. And the item you should be paying most attention to here is that we're running very fast. We inherit the accuracy of Premot and primordial, but again, the key distinction is that we're fast enough to use with MCMC type methods. I want to emphasize that we're not cutting corners to get a fast code. There are no new approximations that we're employing in LINX, and we're crucially not an emulator. We really are solving these physics equations every single time you call the code. And the code is publicly available. It's on my GitHub. I'm also happy to email a link to anybody who's interested. So I thought I would spend a slide singing the praises of JAX in case you're not familiar. JAX is autograd and XLA. Autograd is differentiable code. It means if you write a function in JAX, you get the gradient of that function effectively for free. And so if you're trying to do optimization, for example, it's really easy and efficient if you have those gradients handy. This also opens up very efficient methods for sampling. XLA is accelerated linear algebra. It basically lets you just-in-time or JIT compile your Python code, and so it runs orders of magnitude faster than your ordinary Python code. Now, JAX is a really great option for scientific computing because it looks and feels like NumPy. So to first order, you write all your Python code, you replace your NumPy calls with JAX NumPy calls, and that's it. You've written your JAX code and it'll run super fast. Now, in practice, there are a couple of sharp bits that make it a little more challenging than that, but at least the final product is very readable to other physicists, and so it makes it a great choice for open source codes in physics. And just to give you a demonstration of how fast we're running, this is again the abundances of different light element nuclei as a function of temperature during BBN, and now each frame is a different value of the baryon to photon ratio. So after a roughly 60-second compile time on the first evaluation, all of this data only took about 2 seconds to generate. For comparison, the matplotlib animation took us 10 minutes to generate, and so we are running, fortunately, fast enough to do our parameter estimation. So I mentioned a couple of slides ago that there are some compromises you might have to make if you use some of these other existing codes. So I want to take a closer look at those now. So let's say you're doing parameter estimation, you want to estimate the baryon density and N effective, and you're going to do it with BBN. So let's say you want to do it with parthenopy, one of these older codes. Then the likelihood you write down has to look like this, where in each term for helium-4 and deuterium, you have this constant theory uncertainty. So you picked a value of omega B and an effective, you ran your code a couple of times, you tried your best to vary these reaction rates as nuisance parameters, and you got one value of your theory uncertainty that you now use over all of parameter space. But we found this wasn't a very good approximation. So we checked a pretty humane range of N effective and the baryon density, and we found that the theory uncertainty on deuterium, for example, could fluctuate by as much as 30%. And so what we argue you should do instead is this, where you're sampling your BBN nuisance parameters, you're varying those reaction rates alongside your model parameters. And so what this is effectively doing is computing this theory uncertainty, but now as a function of these model parameters. So when you go through and do this whole analysis, you get a result that looks like this. So there are 2 analyses I'm showing in this plot. The square marker is a fixed and effective analysis. We just fixed it to be roughly 3, and we fit for the baryon density. And the circular markers are showing an analysis where we also allowed N effective to float. The lighter shade error bars are showing the results from an analysis where we used LINX, we used the parthenopy reaction network, and we also used this parthenopy method of using this constant theory uncertainty for BBN. And then finally, the darker shade error bars are showing what happens when you use the same code and the same reaction network, but now you marginalize over all of these reaction rates. And so the results of this analysis were sometimes a 30% reduction in the error bars as compared to previous work. This is not because we're using any new precise data, we're just doing a more sophisticated treatment of the uncertainties during BBN. Now, on the ineffective side, the results are a little bit less pronounced, but given that you really can do precision BBN now, and also given that this analysis only took about 20 minutes, I really see no reason not to be doing the full marginalization, even in this case where you're floating ineffective. So I promised at the beginning of the talk that I'd be able to do a joint CMB and BBN fit. So previously in the literature, people claim to do these joint fits, but really what they're doing is like a really precise BBN analysis, and they use a CMB prior, sort of like what I showed you for that neutrino portal analysis. Or they'll do a really precise CMB analysis and use a BBN prior, or they'll do what Planck does, which is a really precise CMB analysis, and then they do this constant theory uncertainty trick on the BBN side. So what we can now do for the first time is this. So for every value of our common model parameters, in this case, both the baryon density and an effective, we pass these parameters into both our BBN and our CMB code. We will sample the BBN nuisance parameters. Again, this is varying these BBN reaction rates, and we'll pass all of that through our BBN solver to get predictions for deuterium and helium-4. These predictions now encode information about the values of these nuisance parameters that were sampled. We have to pass this prediction for helium-4 into the CMB to be consistent. We'll also sample the other LCDM parameters and the CMB nuisance parameters and pass all of that through a Boltzmann solver. We used class. And then that gives you CLs, which you can use to construct your joint likelihood. You will repeat this process for every value of these model parameters that you want to sample. And so now everything is finally completely consistent. Before I show the results from this analysis, I also want to show what you gain by taking a look at some of these BBN nuisance parameters. So what I'm showing here on this slide is first a BBN-only analysis using the Premot network. So this is the reaction network that has that 2 sigma deuterium tension. And the posteriors here I'm showing are for the baryon density and for the nuisance parameters that control these 3 reaction rates. These are the 3 rates here in red that are most crucial for determining the deuterium abundance. Finally, the numbers on these axes for the nuisance parameters are the number of sigma you are away from the median rate. So pulling a 1.5 here means you are 1.5 sigma above the median rate for this reaction. So here, nothing surprising is going on. You're centered on 0, or you're centered on the median rate for all of these nuisance parameters, and there's nothing terribly alarming going on. But if you now combine with the CMB really prefers these higher values of the baryon density. This is this mild tension. And so you get to see the BBN nuisance parameters pull away from their median values in response to this strong preference. And so you can almost see a future here where you're able to learn about nuclear physics using information from cosmology, rather than the other way around, which is sort of the status quo. And so we don't quite have precise enough measurements from BBN in order to really do this in a way that can match these nuclear physics experiments, but this is something potentially exciting coming on the horizon. And then finally, as promised, I can show my full results. There's not too much quantitative to take away here. It's mostly just a flex. But what I'm showing here is that we can now simultaneously and consistently vary everything. I'm showing the cosmological parameters here in purple. We can vary our CMB nuisance parameters shown here in orange, and then all of our BBN nuisance parameters. That's the neutron lifetime and the individual reaction rates during BBN. This took about 2 days to generate using 192 cores. We used nested sampling, which is just like MCMC, but scales a lot better to these high-dimensional posterior spaces. And what I really want to emphasize is that this long runtime is dominated by class. LINX is faster than class, and so if you want to do an even more efficient analysis, we have now kicked the ball back into the court of the CMB. Now we have some thoughts about how to make the CMB analyses more efficient, but I think I'm going to skip that just because I see I'm running a little bit short on time, and so I'll move ahead to my conclusion slides. So the future is looking bright for BBN. We do need a resolution on whether or not there is actually deuterium tension or whether or not it's going to get larger. I've been hearing some whispers about a new measurement of the primordial helium-3 abundance, and this could be really exciting because helium-3 is sensitive to a lot of the same physics as deuterium, and so it could give us a new handle on this deuterium tension. I'm thinking about some future work. So the analyses I showed in this talk were very model dependent. I was probing specific model parameters. I'm starting to think about other kinds of analyses you can do that constrain thermodynamic histories, which can be used to probe many different models at once. And then finally, I've been working with a collaborator here at NYU, Zilu Zhou, to write a differentiable recombination code, and then also potentially a differentiable version of class. Now, I didn't get to talk too much about why that's so exciting, but I'd be happy to take questions about it either now or over email if anyone's interested. And with that, I'll leave my summary up. I hope I've convinced you that BBN is worth spending some time with, and I can take any other questions now.
Thank you very much. Yeah, any final questions? So maybe I'll just to check quickly. So you're saying the sort of the final error budget is dominated by the measurements of the abundances. Is that a correct statement? In terms of like what would improve your you know, all of your constraints? Is it
good? So I think the thing that is most urgent is getting a handle on which reaction network is the right one to use, because that introduces this quite large systematic, and it's important to get that under control. Next, the most important thing would be to get more precise measurements of the nuclear physics rates that are important for BBN. There are a couple of deuterium rates that, you know, they're measured pretty well, but getting some smaller error bars would give us an even tighter constraint on say, the baryon to photon ratio. And then finally, there's measurement, which also there is still room to improve, and I think is probably the lowest hanging fruit. And so we might expect to see some improvement there first.
Mm-hmm. How much do you foresee things like is your whole setup suitable for like the next stage of CMB experiments? So that these sort of planned measurements of delta N effective down to, I don't know, whatever they're claiming, like 0.03 or something.
Yeah.
Do you expect there to be more issues between then and now that you need to resolve, or is this sort of essentially ready to go to handle that level of precision and effective?
Good. So it's going to depend a little bit on the released likelihoods from these experiments. So SPT, for example, is releasing a fully differentiable likelihood in this package they wrote called Candle. And so you can use these really efficient sampling methods to be able to sample lots and lots of parameters. Otherwise, I mean, if you're just doing this sort of like hand-wavy and effective constraint, it's really easy to just sort of feed that into the pipeline. Basically, I mean, the main bottleneck right now is that the Planck likelihoods are really hard to use. And so if like future experiment likelihoods are also that hard to use, that could be a bottleneck, but there's no like new coding that needs to happen in order to incorporate these things. It's just sort of seeing what these experiments can give us in terms of how they're releasing their data sets and likelihoods.
And yeah, maybe, well, if anyone has any questions, just raise your hand. But maybe I can also ask the sort of the boring nuts and bolts question. So JAX, what is the sort of specific advantage that it's giving you here? Yeah, I mean, you mentioned you know, the autograd and so on, but is there a specific thing that, you know, attracted you to JAX perhaps, or is it's really giving you this advantage?
Yeah, so I mean, there's the fact that it's differentiable, and again, I didn't get to talk about that too much. Maybe I'll just leave this up here. We were able to do a fully differentiable analysis overnight on a laptop, which would have taken a cluster and a week to do otherwise. So when you have these gradients, there is really this huge efficiency advantage. And then the other nice thing about JAX is that one, it's fast, so it compiles your code, and that's independent of the differentiability. And so you can just have compiled Python code, and that's really fast. And then I tend to prefer it over things like Julia, if that's familiar to you. Julia is also very fast and is supposed to look like Python. But JAX literally is Python. It is a package you load into your Python script. and then just use exactly like NumPy. And so it's just the barrier to entry is so much lower, I think, for us as physicists. And so I prefer to use that for any kind of public code at this point.
Yeah, well, you certainly piqued my interest.
I'm glad.
Yeah. All right. Last chance.
I
Yvonne?
just want to make a comment that there is actually a differentiable class code
So,
existing.
so okay, there are a couple of options you can choose. So there's a bunch of differentiable CMB emulators, and that's what we used here in this differentiable analysis. So we used Cosmopower. The trouble with the emulators is that they don't always let you vary all the same parameters as class. So Cosmopower, for example, didn't let us vary like the helium-4 abundance or the CMB nuisance parameters. Now there are other codes that are written in Julia. So there's like Bolt.jl, which the big disadvantage there is that it is in Julia, and so I think the learning curve for physicists is a lot steeper. And I don't believe there's documentation released on Julia on Bolt.jl either, and so I am not sure of its capabilities at this point. So I'm sort of waiting to see this documentation and try the codes out myself at this point.
Do you know about Disco DJ?
I do know about Disco DJ, and Disco DJ
Right.
doesn't give you CLs. Disco
Right.
DJ sort of only gives you matter power spectrum,
Possible.
and we'd
Yeah,
like to
okay,
get
that's
all the
what I
way to
care about.
CLs. Yeah,
Right.
yeah, exactly. It's just it's slightly different interests, and so we think, we want a code that's optimized for new physics and can also give you all the way out to CLs.
Right. Okay, thanks.
Thank you.
Okay, I think we've exhausted all the questions. So yeah, let me